In this video, we're going to look at population proportions, specifically one population proportion. We're going to look at confidence intervals and a hypothesis test for one population proportion. So up to this point in the course, we have worked mostly with means, looking at the mean of a set of data, using a mean of a sample to help estimate what the mean of the population would be, or using information from the sample, the mean from the sample, to conduct a hypothesis test and determine whether we should reject or not reject a null hypothesis. So often when we are given data, we're not always able to take a mean. For example, if I was to poll the class, and if we have 22 students in our class, and 10 of them are full-time students, so then I would have 10 out of 22 full-time students. Okay, so this 10 out of 22 has nothing to do with mean. This is a proportion. 10 out of 22 of our students are full-time students. So that means if I look at this as a percent, 0.455, I rounded to 3 decimal places, are full-time students. This is what we mean by a population proportion, or a proportion in general. It's how many out of a certain sample have a specific quality. In this case, the quality was you attend full-time. So as we look and we define these new variables, when you look at your formula sheet for chapter 12, our new variable is a p. And this gets a little confusing because you want to be careful not to get that confused with a p-value. Okay? A p on its own is a population proportion, and you can think of that as the proportion, or of course the percent, of the entire population that has a specified attribute, the one that we're looking for in our problem. We represent a sample proportion, and this is our p hat. So this symbol with the is going to represent, with the little hat on top of it, it's going to represent our sample population. So it's very important you use the correct P as we're going through these problems. Okay, so as we saw in the last problem, it's if you're given the number of out of that sample that have the specified attribute, it's pretty basic in order to find P hat. All you take is that number. In our case, I said there were 10 full-time students out of a total of 22, and of course is your sample size, and you turn it into a decimal. Now, sometimes when you're going through these problems, you're going to be given a percent, in which case you just need to move the decimal point over 2 places to turn it to a decimal. And sometimes you will be given the sample size and the number that have that specific attribute, and you got to calculate it yourself. So it's going to be different depending on the problem you come across. When we talk about our sampling distribution, it's pretty much very similar to when we dealt with the sampling distribution for the mean. If we took the mean of all of our p hats, all of our sample proportions, the mean of all those p hats would be equal to the population proportion. So this is why our sample proportion is an unbiased estimator of the population proportion. The standard deviation is calculated a little bit differently, and this goes back to, if you recall, what we did with binomial distributions. Our sample standard deviation is going to be our p times 1 minus p divided by n. And of course, you know, we need to have p hat approximately normally distributed for large n's. Now, let's talk about an interval. Meaning, let's look at, sorry, keeps popping up, how we can conduct a confidence interval for our population proportion. Now, this has a lot of similarities. We start with our unbiased estimator, which is our p hat. Okay, we're going to add and subtract, of course, the standard, the z-score, which we're going to be able to get from our table. Everything we do with proportions in this chapter, we're just going to use the z-table. And then, of course, that's multiplied by the standard deviation over n. So here is how we would calculate an equivalent of the standard deviation when we're talking about population proportions. We have our sample proportion times 1 minus that sample proportion divided by n, and then take the square root of that number. Okay, so let's take a look at an example. These examples can all be found in your textbook. This is in section 12.1. It's number 12.49. You can easily find it if you want to try to get on your own. But let's take a look and let's set everything up. Here we have, in the Huffington Post style, in YouGov poll, 1,000 U.S. adults were asked. All right, so there's our N. You know, always write down, you know, and this is what I should be seeing on the work you turn in for your test. You need to write down all the important information and label it correctly. Okay, they were asked about their online versus in-store shopping. One finding was that 32% of respondents never closed shop online. Okay, so our notice in this problem, we are already given p hat, 32%, 0.32. If we were given an x, then you would have to divide by 1,000 to get that p hat. We want to conduct a 95% confidence interval. So we want a 0.95 confidence interval, which means we are going to need a z of 0.05 divided by 2. Also draw pictures, something I didn't see on a lot of your first test. Pictures help a lot. It helps you to visualize what's going on. To have 95% in the middle, that 0.05 needs to be split between the two ends, so you have 0.025. You have areas of 0.025 on each tail. So we need to know what z of 0.025 is, and z, of course, of negative. Okay, so to do that, you can go right to your Z table. You can also, I don't have the T table on here. If you recall, at the end of your T table, you have a list of your popular Z scores that you can use, so you don't need to go through this entire process. But if we try to look up 0.025, you're going to use the negative, of course, and you're looking for an area, so you are inside. And negative 0.025 occurs. Seems to be right here. Okay, there's negative 0.025, and it is at 1.96, or negative 1.96. So we have negative 1.96, and of course it's symmetric, and positive 1.96. So when we look at our formula, go to your formula sheet, always have that formula sheet out in front of you. You are doing one population and you are doing an Z interval. So here is the formula, Z interval for P. Okay, so let's go ahead and plug everything in. We start with our P hat, of course. Our P hat is 0.32 plus and minus that 1.96. And then our, what is equivalent of our standard deviation, this is all under a radical, and we have that 0.32 0.32 times 1 minus 0.32 divided by n, which is 1,000. Okay, so pause the video and I want you to do this calculation on your own. If you are not taking the time to do the calculations, then you're not really watching the videos effectively. You should be doing the work as we go through. So I ask you to hit pause. Try it. Okay, so now that you've worked it out, first thing you can do is just check your answer. Take a look. Did you get your confidence interval lower limit to be 0.291 and your upper limit to be about 0.349? Keeping in mind there are some rounding errors, but if you try to keep everything to 4 decimal places as you're doing the calculations, then you should be pretty close to that number. If you did not get that, then again, you should pause the video right now and take a look at the steps I have and the work you did to make sure that you can arrive at that answer. And also don't forget your interpretation. There's always an interpretation in a confidence interval or a hypothesis test. So the interpretation here is basically we can be 95% confident that the proportion of adults that do not shop online is between 0.291 and 0.349. Of course, you can also state this as a percent. We can state, to be a little more easier to understand, we could be 95% confident that the percent of adults that do not shop online is between 29.1% and 34.9%. When you interpret, you want to write it in the most kind of user-friendly language as possible. Okay, so let's move on and continue with this video with a couple other things. The idea of margin of error is exactly the same. Okay, our margin of error is, of course, that part of the formula that's after the plus and minus. So the z of alpha over 2 times the sample proportion, 1 minus the sample proportion over n square root, is this part of our formula, okay, as it's always been. So in the problem we just completed, think about that for a second. What is the margin of error? The margin of error, of course, is this 0.0289. Just like in other confidence intervals with one population of means, you can also estimate your sample size needed in order to have a smaller margin of error. This is a little bit trickier, and I'm going to guide your attention first to this formula. We're not going to spend a lot of time on this. But the problem here is you just don't know what your sample proportion is because you don't have it. And you need that sample proportion. So you can make a guess. If you feel pretty confident that your sample proportion is going to be about 75%, then you can guess 0.75. So this P sub G is just a guess. If you have no idea, then the idea here is to set it at 0.5. Okay, so 0.5 is your middle ground, 50%. When you do that, if you were to put both of them at 0.5, 1 minus 0.5, of course, is 0.5 again, what you get is 0.25. So a general formula, if you can't make a guess, is just to use P times 1 minus P to be 0.25. And then you can estimate. Again, you might see one of these problems in your homework, but we're not going to spend much time on that. I do want to take a look in this video also at the hypothesis test. So hypothesis test, again, is very similar. Couple assumptions we have to make when we conduct a hypothesis test for proportions. Of course, you need to have a simple random sample. And the other part is, and this one's a little tricky, but either your n times your proportion or n times 1 minus your proportion has to be greater than 5. So you have to have at least 5 data values in either that attribute you're looking for or at least 5 data values not in that attribute you're looking for. And this, for most of the problems we're going to do, we can hold these assumptions true. But you might come across one in your math lab where that n times p sub o was not 5. So if you recall, p sub o is our null proportion. This is what we kind of assume to be true. This is the one we're testing against. Okay, so that null hypothesis, whatever p sub o is that part of the problem that we're testing against. And we'll take a look at that when we look at some examples. Your alternative hypothesis is very much like before. You could have a two-tailed where it's not, we're testing it that it's not equal to that it's different. We're testing that it's less than, so a left-tailed, or we're testing that it's greater than for a right-tailed. Of course, there'll be a significance level. And here is our basic test statistic formula. Again, very similar. Normally we have our sample mean minus our population mean. Now we have our sample proportion minus our population, what we believe that population proportion to be. And then keep in mind it's that population proportion you are using to calculate the equivalent of that standard deviation, which in this case is p sub o, 1 minus p sub o over n. So let's go ahead. Finishing the test, just like before, once you get that test statistic, the hypothesis test is going to work exactly like one mean hypothesis test. You can do either a critical value or you could do a p-value approach. And we'll do both approaches. And of course, don't forget to interpret. We'll do both approaches in this sample problem right here. So here we have a phone survey was conducted of 758 Arizona adults. Well, there's your N. N equals 758. Let's write that down. Who celebrate Christmas. So these are adults who celebrate Christmas. The question was asked, in your family, do you open presents on Christmas Eve or Christmas Day? Of those surveyed, 394 said they wait until Christmas Day. So that is the attribute we're looking for. That is our X. So we have 394. So we want to determine and interpret that sample proportion. Okay, let's do part A first. Your sample proportion, or P sub hat, of course, is going to be X over N. 394 over 758. So you can go ahead and calculate that. And we can round that to 0.52. Because if I round the 9, the 9 is going to go up, so let's round it to point. I'm really rounding it 3 decimal places, which actually makes it 0.520 in this case. So you do want to round these about 3 decimal places. Okay, so part B. At the 5% significance level, well, there's our alpha. Do the data provide sufficient evidence to conclude that a majority? All right, so you're not always going to have that more than 50%, but as soon as you hear the word majority, you're testing it against the 50%. So this is where you have to kind of read your problems carefully. And we're looking to conclude that a majority of Arizona families who celebrate Christmas wait until Christmas Day to open their presents. So that means we are testing against our P sub O, in this case, is 0.50. Okay, and we are checking if our sample proportion has enough evidence in our sample that that proportion is actually, we can feel confident and conclude that it is, that the population proportion is greater than 0.50. Okay, so we have all of our information. We need to go back. So let's look at our formula sheet to find our formula. So now we are doing a z-test statistic when p equals p sub o. So whenever you see that and you have a p sub o in your problem, you're doing a one population proportion test. So that is the formula we're going to use, p minus p sub o. Let's go ahead and write it out. Sorry, my paper went, I gotta scroll back, apologize. Here we go. And let's fill in the important information. So looking at your formula, our z-test statistic is going to be 0.520 minus our p sub o, which is just 0.50 in this problem. And recall that in this formula, you're going to use that p sub o times 1 minus p sub o divided by 758. Okay, so again, this is where you're going to hit pause and you're going to attempt to do that calculation on your own. Everything in the denominator is under a radical sign, so you don't take the square root until you do 0.5. So you should get 0.25 divided by 758. Figure that out first, then take your square root. Go ahead and calculate that, and then unpause your video. And hopefully you got 1.10 for your test statistic. Now, as I stated, we're going to do both a critical value and a p-value approach so that you get practice with both of them. So let's come down here and let's first do our critical value approach. Always, always draw your picture. This is a right-tailed test. Okay, so what we need is the z-score. Remember, this is 0.05 is the area in here because that is our significance level. And we need the z-score, z of 0.05. So please look at your formula sheet, find z of 0.05, and place it here. This is your critical value. It is 1.645. Okay. This test statistic of 1.10 clearly falls to this side of 1.645. This is your test stat. So we are going, in this case, this would be a do not reject. Let's also look at that p-value approach. Again, draw a picture. This time, when you do a p-value approach, the main difference, of course, is in a critical value, we are comparing the numbers and where they fall along that horizontal axis. But in a p-value approach, we're looking at areas, and we are going to compare areas. So when you do a p-value approach, it's your test statistic that goes here. It's not your critical value. It's your actual test statistic. And what we want is the area, because it's a right-tailed test, to the right of that test statistic. So to get that area, we can use our formula sheet. This is a z-table, so it makes it a little bit easier. I mean, we can use a z-table, so it makes it easier. So our test stat is 1.10. Take a look. If you go to 1.10, we were trying to find that area, 1.10. It looks to be about 0.8643, but keep in mind, of course, that this is the area to the, I don't have the picture up here, but it clearly is the area to the left. Sorry about that. I don't know why I did that. You can look at your sheet above. This is the area to the left. We don't want the area to the left, so you can do 1 minus that, or if you want, you can just use the this idea of symmetry and do 1.1 over there. And if you do 1 minus it, if you go to the negative, it's going to be 0.1357, which is what your p-value is. So this area, this p-value is 0.1357. So what do we compare it to? We compare it to alpha. Alpha in this problem is 0.05. And you set up an inequality and you tell me, oh, my p is definitely greater than alpha. This is what I should be seeing for the work on your test. Compare p to alpha. P is greater than alpha. And because p is greater than alpha, once again, we do not reject. If you do both approaches, they always will come out the same. Okay, you can't get one to be reject and one to be not reject. And then our interpretation. your interpretation goes back to this statement. A couple things I always want to see in an interpretation. First, what's the significance level? So you need to state at the 5% significance level. Okay. So the question is, do the data provide sufficient evidence? So is that a yes or a no? We did not reject, which meant our data do not provide sufficient evidence. Okay, so that's the second important piece. The third part is put it in the context of the problem. You cannot end there. You can't just say to reject and be done. No. Sufficient evidence about what? To conclude that Arizona families who celebrate Christmas wait till Christmas Day to open their presents. You can certainly summarize it. Wait until Christmas Day, sorry, it's sloppy, to open presents. If you think about it, all you're doing with this conclusion is simply restating the statement and the question that you were asked, with your conclusion embedded in it. Okay? So thank you. In the next video, we will look at doing a proportion test for two populations.